Okay guys, so today we're going to be talking about graphing quadratic functions. It's also our introduction to quadratic functions. And a quadratic function in general form looks like our blue box here, which is y equals ax squared plus bx plus c. Okay, where if x squared is the highest power on x, we're going to have a quadratic function. Okay, so its graph, you might remember this. You've probably seen it before back in Algebra 1. The name of the shape of the graph here, this U shape, is called a parabola. There's some parts that are important on our parabola. One of them being kind of the maximum or minimum. In this case, it's the minimum y value on my graph down here is our vertex, which is located at hk. And this is normally be like x and y, but we already have an x and y used in our equation, so we're using h and k for the x and y coordinates of the vertex. Then we have this point, or this line, I should say, sorry, that comes through the middle called the axis of symmetry. Okay, our graph is symmetric, as if you were to reflect one half of our graph over that line, it would go on top of the other half. So it's an axis of symmetry, and that's located at the equation x equals h. Okay, so in our general form, it's not easy from the equation to tell where that vertex would be, that lowest point. Okay, one of the ways to calculate our vertex is we have a formula here. To get the vertex, h, which is the same thing as the x coordinate of our vertex, is equal to the opposite of b, so negative b, all divided by, I should say, 2 times a. So negative b, or opposite of b, all divided by 2a. Okay, the y coordinate we can get, so in this case k, which is the y coordinate of my vertex, we can get by plugging h into our quadratic. Okay, so we can use this formula to get the x coordinate of our vertex, or this is like x, and then we can plug that value into our function for x to get y. Okay, so this gives me the x coordinate of my vertex, this gives me the y coordinate of my vertex. Okay, there is another form that we commonly see quadratics, which is called vertex form. Okay, vertex form is very nice because, as the name sounds, it gives us the location of the vertex just by looking at the equation. So we don't have to do the opposite of b over 2a and plug back in. We can actually identify them from these h and k values here. Okay, where this h value is going to give me the x coordinate of the vertex, and k out here gives me the y. Now, one part that can throw some trouble in here, though, is that it is x minus h. So, in other words, if you see something like this, x minus 4, let's say in that part, h is actually positive 4. The minus is part of the formula there. So there, h would equal positive 4. If you were to have something like x plus 2 squared, here h is actually negative 2. You could actually even think of this as being x minus negative 2. So that's our minus h. So here h would be negative 2. Okay, so a mental shortcut that might help is that h is kind of the opposite of sign of what it appears to be, and then k is the same. We don't have to do anything special for k there to identify our vertex. Okay, so let's try some examples here. It says, find the vertex and the equation of the axis of symmetry for each of the following. So our first one, I noticed that this is in the vertex form. They've given me this nice form with h and k visible, so this should help me find our vertex pretty easily here. Okay, so remember that we're looking here to get h in our quantity squared, but h is the one that's kind of the opposite of what it appears to be. So here h is actually negative 4. Okay, and our k value is whatever after our quantity squared that's being held with addition or subtraction. So in this case, negative 6. So k is negative 6. Okay, so our vertex is located at negative 4, negative 6. And the axis of symmetry, which we'll use AOS, is this vertical line x equals our h value. Since our h value is negative 4, that's what we put. So there it is. There's my vertex. There's my axis of symmetry. And that is an equation. So please write x equals negative 4, not just negative 4. It's not a single value. It's an equation of that vertical line, x equals -4. Okay, let's try our next example. For number 2, I notice this time our equation's given to us in general form. So we can't immediately identify that vertex. We're going to have to solve for it using these formulas that we saw in the middle here. So let's start by doing that. Let's find h, which is equal to the opposite of b over 2a. Okay, and in this case, this is our a value. Our a value is 2. Our b value is -12. And our c value is +24. Okay, so remember that it's opposite of b, so the opposite of -12 is +12 over 2 times a, so 2 times 2, our a value is 2. So we get 12 over 4, which gives us 3. My h value is 3. Okay, to find k, the y-coordinate, we need to plug in 3 into our function. So we need to find, so we're going to say k equals f of 3. So plug 3 into our function. 2 times 3, 3 squared minus 12 times 3 plus 24. So again, order of operations, remember exponents before you multiply. So we're going to have 3 squared, which is 9. It's a 9 there. Minus 12 times 3 plus 24. Now we can multiply 2 times 9 is 18. -12 times 3 is -36 plus 24. 18 minus 36 is -18 plus 24 is +6. Okay, so I didn't leave myself a whole lot of room here, so maybe I'll just try to squeeze in over here. We do have a third example to get in here. So my h value ended up being 3. My k value, which we just solved for, is 6. So I know my vertex is located at 3, 6. And my axis of symmetry is located at x equals h. And our h value was, that's not a 3. X equals 3, there we go, our h value. Okay, so far so good. Let's go through one more example here. So once again, unfortunately, we're given an equation that's in our general form and not vertex form, and we want to identify the vertex. So let's once again use our formula, the opposite of b over 2 times a, where my a value is 2, my b value is also 2, and my c value is +3. So we have the opposite of b, -2, it's the opposite of +2, over 2 times a, and a was 2. So we get -2 over 4, which reduces to -1/2. Okay, to find my k value, now we need to plug in -1/2 into my function. So we're going to have 2 times -1/2 squared plus 2 times -1/2 plus 3. Okay, again, exponent first. So -1/2 times -1/2 is +1/4. Remember, think about multiplying fractions top times top, bottom times bottom. We should get 1 over 4 there. Plus 2 times -1/2 plus 3. So again, just our exponents in that step. Now we can multiply. You can think of this as 2 over 1. We get 2/4 or 1/2. Here, again, you can think of that over 1. We're going to get -2 over 2, which becomes -1. Or in fact, maybe I'll leave that as 2 over 2, just so we have a common denominator to help us combine here. And in fact, our 3, just to give it a common denominator here, let's multiply top and bottom by 2. Because remember, when you add or subtract fractions, you need a common denominator. So since I knew I was going to have a 1/2, kind of made these have a common denominator of 2. So 1/2 minus 2/2 is -1/2. Plus 6/2 is 5/2, or 2.5 as a decimal. So my vertex is -1/2, or -0.5, and +5/2, +2.5. And our axis of symmetry is x equals -1/2. Okay guys, this next part you don't need to write down for these next kind of 2 slides. This is really just going to help explain patterns of parabolas. That's going to make these a little easier for us to graph. than having to plug and chug a lot of values. Okay, so below here we have the parent function y equals x squared. We have that's a pretty bad rectangle. We have our regular parabola or parent function parabola graphed here. Okay, so one thing to notice is some of these nice lattice points or integer points that are on our graph will follow a pattern. So specifically, our pattern here is that my y value, or my vertical movement, my y movement, is equal to my x, or horizontal movement, squared. Okay, now this is only true for the parent function, but we're going to learn how to apply this to pretty much all parabolas we want to graph. Okay, so in other words, if I start at my vertex, and that's one of the places we will always start graphing our parabolas, if I were to go left or right 1 unit, okay, so my x value is 1, we're going to end up going up that value squared. So 1 squared is 1. So if I go left or right 1, we go up 1, and you can see we find those nice lattice points. Okay, in my second figure here, we're going out a distance of 2. So if we were to go left or right 2 from our vertex, we need to go up that distance squared, and 2 squared is 4. So you would go up 1, 2, 3, 4, and you can see if you do that on either side, we run into our next points. Okay, and then following that same pattern, if we go left or right 3, so we go out 3 here, we would go up that distance squared, and of course 3 squared is 9, so you'd have to go up 9 units. You can see that up there at 3, 9, and negative 3, 9, our next 3 points. Okay, so that's true for our parent function. We're going to look at some values that will do things like flip my graph upside down, etc. here. Okay, one of our other transformations that's going to happen to our graph is if my a value, so that's the number in front of x squared, if a is negative, we get a graph that gets flipped over at its vertex. So it's going to be flipped upside down, essentially at its vertex. So not only because this is negative, it's going to be upside down, but this 2 is also going to double the vertical distance. So double the up and down movement. So for instance, on my parent function, we said if you go left or right 1, right back up here, if we went left or right 1, we go up that distance squared. Okay, well now, because it's got a negative a value, we'd be going down. So if I went left or right 1, I should normally be going down 1. Okay, I would normally have a point right here. However, that 2 is meaning we're going to double that vertical distance. So instead of going down 1, we go down twice as far to find our next point. Okay, that 2 is giving what's called a vertical stretch by a factor of 2. Okay, so if we were to go out, say, 2 units, like in our next picture here, we would normally, like in our previous picture here, we'd normally be going up or down 2 squared, or 4. But remember that we are doubling this distance. So we're going down 1, 2, 3, 4, 5, 6, 7, 8 units before I find my next point. And if I tried to go left or right 3, so you can imagine if I try that with a different color here, if I say I went left 3, 1, 2, 3, well 3 squared would normally be 9. So I'd normally be going down 9, but this is doubled. So it would be like 18, which would be way off my graph. Okay, so let's try one more of these, and then there is a part actually on our next slide we'll need to write a little bit down on. Okay, so one more example of kind of using this pattern and how it will save us some time here. So below is y equals 1/2 x squared. Okay, so this time it's positive, my graph is opening up, but we're only going to go up half the vertical distances we normally would. Okay, we also call this a vertical compression, and we'll write a little bit of this down in a second. Okay, so if I start with my vertex and I go left or right 1, remember we normally go up 1 squared, or 1. However, not only am I doing that, but I need to multiply that distance by 1/2. We're only going up half the distance I normally would. So instead of going up 1 full unit, we only go up 1/2. Okay, if I go left or right 2, okay, 2 squared would normally give us 4. So on my normal parabola, we'd be going up 4 units. We'd be up here. Okay, but as you can tell, we're only going up half that vertical distance. We only go up or down 2. Okay, and then lastly, if I were to go left or right 3, okay, 3 squared would be 9, but we only want to go up half of 9, which is 4.5. So we go up 1, 2, 3, 4 and a half units to find our point there. Okay, so we can use this to help us find some values where we don't have to necessarily plug in a whole bunch of x's and calculate a whole ton of y's. This pattern will help us out a little bit. Okay, there are a few things that we do need to write down that we didn't write down on our previous slides. So let me pop some of that up here for you. Okay, so these are the two forms that we saw earlier. I've just written them here for easier access. Okay, so we have our standard form over here, our vertex form, quadratic over here. Okay, so it's important to know that the a in front of both of these is the same value of a. Okay, if that a value is negative, our graph is going to be flipped upside down. Okay, we would say our normal U-shaped graph opens upwards, that parabola, and if a is negative, it would open upside down. We'd say it opens downwards. Okay, but we'll see a lot throughout the year, and it will mean our graph is flipped upside down. Okay. If the absolute value of a is greater than 1, meaning if we have any values like 2 or -2, 3 or -3, so regardless of its sign, whether it's positive or negative, if the digit is bigger than 1, okay, our graph will be vertically stretched. If my normal graph looked something like this, and my a value was 2, it would look a little thinner. It would look like it's been stretched vertically. So imagine pulling something that would stretch in the vertical direction. Okay, if, however, a is a value that falls between 0 and 1, so this happens with decimals that are between 0 and 1, or fraction values like 1/2 or -1/4, and again, we're talking about its absolute value, so it could be positive or negative. Remember, that only controls whether it opens up or down, the positive or negative sign. But if its value falls between 0 and 1, our graph will be vertically compressed. So imagine taking a graph that looked like this, and we kind of compressed it in the vertical direction. It ends up looking a little wider. Okay, so it'll look wider than our parent function. This really only applies to our version that has h and k in it right now, but we can talk about those from the origin, from our parent function. H is going to shift my graph left or right, and k is going to shift my graph up or down. And we'll see those a, h, and k show up in a lot of functions throughout the year. So we're just introducing it now with parabolas, but we will see those a lot. So it's important to know a is negative, it flips my graph upside down. If a, regardless of its sign, if the digit's bigger than 1, we get a vertical stretch. Okay. If a is between 0 and 1, we get a vertical compression, which makes it look a little wider. H will shift my graph left or right, and k will shift my graph up or down. Okay, so let's try graphing some of these. A few examples here. Graph each of the following. Label the vertex and axis of symmetry on our graph. Okay, well, luckily our first one here is given to us in vertex form. So we can quickly identify my vertex at our values of h and k. However, remember, h was a little tricky. The minus sign was part of the formula. So our h value is actually 1. Okay, so h is really positive 1 here. My k value, there's no tricks with that. That is just 6. So my vertex is located at 1, 6. And in fact, we can even graph that to help ourselves out. Go right 1, up 6. There is my vertex of our graph. Okay, some other key characteristics to look at is our a value. Okay, here a, that multiplier in front of our parentheses, is -2. Okay, so remember, negative means it's flipped upside down. So we're going to have an upside down looking parabola, something that's upside down. And because its value is greater than 1, it is vertically stretched by a factor of 2. Okay, by a factor of whatever a is there. So this guy's going to be upside down and stretched by a factor of 2. Okay, so what I would normally do from here is I would draw in my axis of symmetry, which goes right through the vertex, since we've already plotted that. Okay, we can sketch that in, and I can label below here that my axis of symmetry is the line x equals 1. Remember, it's the same as our h value. Okay, we've got our axis of symmetry, so my graph should be symmetric around that line. So now we're going to find some more points using our pattern. So let's see, if I go left or right 1 unit. Okay, normally I would go up or down that distance squared. So we'd normally be going, say, down 1. However, remember my a value is 2, specifically -2, so we are going down, and we're going to go down twice as far as we normally would. So if we were to go left and right 1 unit, we would go down, instead of 1 squared, which is 1, we go down 2. So we're actually going to go down 2 on each side. If I were to go left and right 2 units, now 2 squared is 4, so we're normally going up or down 4, but remember we are going twice that distance. So in this case we are going down 8 units. So left or right 2, I'll go right 2 and go down 1, 2, 3, 4, 5, 6, 7, 8 units, and I can go over to this side and find my symmetric point. Just kind of using that axis of symmetry to help me quickly find the other one. And if I did try going out 3 units, 3 squared is 9. So I'd normally be going down 9, but we would be going double that distance this time, or 18, which would take me a couple points off my graph, probably roughly here, if it were to fit on my graph. So then we can draw in our parabola. Okay. By the way, while I'm doing this, the reason the axis of symmetry is dashed and not a solid line is it's not technically, that's a really bad line, it's not technically part of the parabola, it's just an aid on my graph. So let's also label our vertex and ask us to do that in the directions on the graph. So 1, 6. Okay, there's our first example. All right, our second example. Luckily, again, this is in that vertex form. So let's first start by identifying our vertex. Okay, so we'll look over here to find our h value. And again, remember h is kind of the opposite of what it looks like. So that is +4 for my h value. And my k value over here, there's no tricks with. So that guy will just be -2. So k is -2. So my vertex should be located at 4, -2. So we can start by graphing that, right 4 down 2. There's my vertex. And I can even graph in the line of my axis of symmetry, which should be x equals 4. Always goes vertically straight through our vertex. So I can graph that wherever I'd like. I guess I'll use this open space down here. Axis of symmetry is x equals 4. Okay, so before I label my vertex or add some more stuff in there, let's figure out what else is going on with our graph. Okay, and a is going to tell us most everything else we need to know. So a is 1/2. So because it's positive, it has not been flipped upside down. It's going to go up like a normal parabola would, but it is going to be vertically compressed. So I ran out of room, but compression there. And it is vertically compressed by a factor of 1/2. So let's think about that. We did a very similar example on one of the previous slides, which is if I were to go left and right 1, instead of going up or down that distance squared, going up or down 1, we only go up or down half of that distance. So we only go up or down 1/2. Okay, to find our next points, when I go left or right 2, we would normally be going up this distance, or 2 squared. We'd normally be going up 4. However, we are only going up 1/2 of that distance. So we go up 2 rather than 4. When we go left or right 3, 3 squared would be 9. But instead of going up 9, we go up half of 9, or 4.5. So up 1, 2, 3, 4.5. And my symmetric point here. And I could probably fit in one more. If we go left or right 4, which would bring me way out to here, we would go up 4 squared, or 16. Okay, but we're only going up half that distance, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Apparently somebody thinks it's a drag race out here. Sorry about that. So here is my parabola. Pretty poorly drawn, but it should look something like that. And we'll label our vertex 4, negative 2. Okay, we got one last example here. Okay, this time we do have to do some extra work up front. So you can tell we have this in standard form, not our nice vertex form. So we need to calculate our vertex. So remember that h is the opposite of b over 2a. And in this case, remember a here would be 2, b is 4, and c is negative 3. So the opposite of b is negative 4 over 2 times a, which is 2. So we get negative 4 over 4, or negative 1 for our x coordinate of our vertex. Then to find k, we need to plug in h into our function. So let's plug in, I can actually just put in the number there, negative 1. Let's plug in negative 1. 2 times negative 1 squared plus 4 times negative 1 minus 3. So negative 1 times itself twice is positive 1. Now we can multiply. 2 times 1 is 2. 4 times negative 1 is negative 4. And then subtract 2 minus 4 is negative 2. And negative 2 minus 3 is negative 5. So if we did all of our math correct there, my vertex should be at negative 1, negative 5. So left 1, down 5. There's my vertex. And now I can sketch in my axis of symmetry here at x equals negative 1. Okay, so my axis of symmetry is x equals negative 1. Okay, now we can use my a value to help fill in the rest of our points here. So a here is positive 2. So it has not been flipped upside down, but we do have a vertical stretch by a factor of 2. So this thing's going to be taller than normal, which makes it look thinner. So again, following our pattern, instead of going, when I go left or right 1, I would normally go up or down that distance squared, 1 unit. But in this case, when I go left or right 1, I need to go double that distance upwards. So we go up 2. When I go left or right 2, we'd normally go up 4, but I need to double that distance. We go 1, 2, 3, 4, 5, 6, 7, 8, way up here in my symmetric point. And if I went left or right 3, we'd normally be going up 9, but double that 18 does take me way off my graph. So I think this is all the nice whole points that I can fit on my graph here. And I never do a good job of making those look rounded down there. And it's pretty hard to draw on a tablet and keep my pen lined up, so bear with me here. Something like that. Okay, so there's my other graph. The last thing that I don't think I mentioned earlier is in my graph, when it's in this standard form with a, b, and c, not in vertex form, this constant c ends up actually giving us the y-intercept. Equals negative 3, not positive 3. So in standard form, the constant at the end does give your y-intercept a little extra part to help make sure our graphs are correct. Okay, so last, let's end with a word problem here that will have to do with our lesson today, and quadratics and parabolas. It says the profit from selling tickets at the Smith Center depends on the ticket price. Using past receipts, the owners have found that the profit can be modeled by this function. P of x equals negative 15x squared plus 600 times x plus 60, where x is the price of each ticket. Okay, so they just defined x for us. What is the ticket price? If x is the price of each ticket, what is the ticket price? So they're basically asking me, what is x? That yields the maximum profit. Okay, well, profit is modeled by this function, so P of x that gives the maximum P of x or a y value. So what is the ticket price? What is the x value that yields the maximum profit or y value? So let's use what we talked about today to think about some things about our graph. Okay, so remember that this a value is the same in both forms, even though this quadratic is in our standard form with a, b, and c. But our a value is negative 15. So we know a couple things about my graph from there. Negative means it's been flipped upside down over its vertex. And the negative 15 means it's very, very stretched. It's like super stretched in the vertical direction. Probably even thinner than that. You might have imagined we're really zoomed out here. Okay, so it's an upside down graph. And we're graphing, of course, if these were our coordinates. It doesn't matter exactly where they're at here. But X is our ticket price. Whoops, I don't know what happened there. Price, okay. And then our Y value is our profit. Okay. So what is the ticket price that yields the maximum profit? Well, if my profit is my Y value, the maximum profit is going to end up being at our vertex. So we need to find the X coordinate of our vertex, which has to do with the price, and the Y value, which has to do with the profit. Price, which is X, and profit, which is Y. So in other words, we need to find our vertex. Okay, and since it's in standard form, we're going to use our values of A, B, and C to calculate our vertex. So remember that H in this form is the opposite of B over 2A. So the opposite of B would be negative 600 over 2 times A, which is negative 15. So simplifying the bottom, we get negative 30. And when we divide this, we end up getting positive 20. So we now know that the H value, or X coordinate, is 20. Okay, so in fact, that is the price that will yield the maximum profit. So in fact, we've actually already answered the first question. What is the ticket price that should yield maximum profit? $20. The second part, though, says, well, what is the maximum profit? Okay, so now we basically need to find Y here, or K. So remember that to find K, we need to take our function and plug in the value we got for H. So plug in 20. So we're going to have negative 15 times X squared, or 20 squared, plus 600 times X, 600 times 20, plus 60. Okay, so some math to do here. 20 times 20 is 400 for our exponent, plus 600 times 20 plus 60. Multiplying here, negative 15 times 400 is negative 6,000. 600 times 20 should be 12,000 plus 60. Negative 6,000 and 12,000 is 6,000. Plus our 60 gives us $6,060. So our maximum profit, so we have a maximum profit of $6,060 when the ticket price is $20. All right, so there's a nice word problem that has to do with our parabolas, maximizing a function that we can find with a quadratic. Maximizing or minimizing is actually used in business a lot. So there's lots of similar questions like these. So thank you guys that stuck around for the whole thing. That's a lot of notes for today, but it's all pretty important. It will definitely help us out as we visualize what we do as we work with quadratics.